This figure is to highlight an important concept that I would like to discuss now, which is the relationship between disease prevalence in a specific population and the positive and negative predictive value of a test that's used in that same population. And what this is illustrating is that as the prevalence of the disease, which is represented on the x-axis, goes up, there's a trade-off between the negative and the positive predictive value of a screening test, where the positive predictive value is illustrated here in the dashed black line, and the negative predictive value is the solid black line. So essentially what is being shown is as prevalence increases, we see an increase in our positive predictive value of our test, and essentially kind of some leveling occurring. And the reverse is occurring with our negative predictive value, and that is disease prevalence increases, the negative predictive value goes down. Now, rarely do we ever see a disease for which there's 100% prevalence of it in a population. And similarly, we wouldn't even screen a disease if the prevalence was zero, right? It goes back to that earlier point that there must be a significant public health problem for screening to be utilized. So essentially, the use of a screening test that's going to yield negative and positive predictive values having any meaning would be those diseases that have prevalences around 30 to say 60%. And that is where we have a reasonably acceptable positive predictive value that climbs actually with increasing prevalence, but we don't have too much of a loss of the negative predictive value. So this is an example of how the prevalence affects our measures. So on the left-hand side, we have a scenario where we have a disease that has a prevalence of 4%. And on the right-hand side, we have the same disease, but for which the prevalence in that population is only 1%. We're dealing with the same number of individuals, 1,000 in each example. So given 1,000 persons and a prevalence of 4%, we know we have 40 people with the disease. And we're now dealing with a test that has a 90% specificity, a 90% sensitivity and a 95% specificity. And by the way, sensitivity and specificity are not influenced by prevalence of disease. So these two measures are the same in both scenarios. So we can use those values now to calculate our true positives, which would be 36 or 40 times 90%. And we can calculate our true negatives, which would be 912. And from there, we can calculate our positive and negative predictive values by filling in the other two cells. And in this case, we get a positive predictive value of 43% and a negative predictive value of 99.5%. When the prevalence is only 1%, or fourfold less than this example, you see here that the positive predictive value now drops by threefold. It's 15.3. However, the negative predictive value stays high. It stays around 99%, and that is because the overall prevalence of disease is very low. But here you're shown a very clear example of how with just a drop in prevalence from 4 to 3%, you see a drop in the predictive value from 43% to 15%. So again, prevalence influences the predictive value, both positive and negative, of a screening test. So what we do in scenarios where prevalence cannot be estimated from a study, or if we're dealing with data that is constrained by sample sizes such that we don't believe the prevalence that we're generating from that sample, we calculate what's called an adjusted predictive value. And what we're doing is we're using background estimates of prevalence to calculate our adjusted positive and negative predictive values. And the equations are shown here. I'm not spending a tremendous amount of time on this in the class, but suffice it to say, if you're dealing with a situation where you have low numbers, small numbers, it is possible to utilize a background prevalence value to calculate your positive and negative predictive values, if you can assume that the prevalence in this small population that you're calculating the predictive values of your screening test are held constant to that from the background. So here is an example going back to that glaucoma and intraocular pressure situation. And in this case, this example is showing how the predictive values are being affected by assuming different prevalence values from background sources. So in this side, left-hand side, we have 20% prevalence assumption, and on the right-hand side, we have a 40%, and it's showing you how the adjusted positive predictive values turn out versus the unadjusted. And you see here that there's not as much of a change in the adjusted prevalences, positive prevalences, as the population prevalence doubles. So the next concept I want to discuss is called a likelihood ratio, and these are another way to calculate probability of disease given a test positive without accounting for prevalences. But unfortunately, these don't generate values such as we get from the positive and negative predictive calculations. Instead, we get a value that we have to interpret in terms of its size. So it's a relative measure. So the likelihood ratio for a positive test is the probability of a positive test for a person with the disease over the probability of a test positive among a person without the disease. And the larger the size of that value, the better the diagnostic value of the test or screening value. Generally, a likelihood ratio greater than 10 is considered a good test. And then the reverse is shown below for the likelihood ratio of a negative test. And here the value that's used as a measure is 0.1, such that a value of 0.1 or less is considered a good test for negative predictive values. And here is the way that the likelihood ratio positive and likelihood ratio negative values are calculated, and they're functions of the sensitivity and the specificity of the diagnostic, so they don't rely on the prevalence, as I said before. And then here is an example going back to the one I showed earlier where I had different prevalence values. So all I've added here are the likelihood ratio values, which don't change despite the change in the prevalences. So again, just another way that we determine the predictive probability of a test to identify persons who have the disease. And the likelihood ratio test would be a value that would be useful from a clinical perspective, just as the positive and negative predictive values are.